Okay, so you should have done your warm-up. I don't think that there's anything really unusual here. Just, pay attention to the words there. Some of you don't always read very well to notice that it says it's normal. I just plugged them all in the calculator and I used the calculator. And what kind of error could I have made? Well, since I reject, I could have made a type 1. And it only asked me for the consequence. I took it a little too far, went dark here, so, but there's my consequence. Alright, today what we're doing is really not too different from what we did yesterday. We are just looking at all this stuff now for matched pairs. So, some new notation. So we have the difference in population mean. So this is the true, and when I say difference in population means, what I really mean is from a matched pair perspective, the true difference in two values. So like you have a pre-score and a post-score. And if I had everybody in the population and I subtracted all those values, and the mean of all those differences is mu d. The differences of the sample mean is x bar d. The standard deviations, I'm going to avoid double subscripts here, so I'm just going to say SD. The standard error, SD over the square root of n. Okay? Your test statistic. So x bar d, so that's the statistic minus the parameter divided by the standard error. Okay, the standard deviation of the statistic. All right? Okay, this first problem right here. So we want to know which lane was faster in the supermarket, the express lane or the regular lane. To collect their data, they randomly selected 15 times during a week, went to the same store, and bought the same item. However, one of them used the express lane and the other used the regular lane. To decide which lane each of them would use, they flipped a coin. If it was heads, Libby used the express lane and Catherine used the regular lane. If it was tails, Libby used the regular lane and Catherine used the express lane. They entered their randomly assigned lanes at the same time and each recorded the time in seconds it took them to complete the transaction. So this is a matched pair because what they're doing is they're picking one time slot. So let's say they go 10 a.m. and one of them does the regular lane and then the other one does the express lane. Then they pick another time slot and they did that 15 times. It's not like they treated this two separately, where Libby went to the grocery store wherever and maybe one of her times was 10 a.m. and one of her times was noon and one of them was 3 p.m. And then Catherine went maybe at 9:30 a.m. and she went at 12:30 and then she went back at 1:30 p.m. So it's not like they took their time separately. They picked one time and then did two things during both times. So that's why it's considered a matched pair. If they did it this way, it would be considered a two-sample procedure. That's not what we're doing. All right, so here's their data. We want to carry out convincing evidence to see that the express lane is faster. So I want to know if the express is bigger than the regular, or the express minus the regular is greater than 0. So what I'm going to do here is so if this is backwards. If the express lane is actually greater, if the express lane is actually faster, the time is less. So then the express minus regular is actually less than 0, because if you're faster from a time perspective, then your time is less. Okay, so I'm going to do this one a little differently than maybe I have in the notes that I filled out online. So I'm going to define mu d as the true mean difference in seconds of the two lanes. And I'm going to say here that I am doing express minus regular, okay? Then I'm going to come over here and I'm going to type all these values into my calculator, and then I'm going to use that list 3 to do express minus regular. And so this is where, like, if you're just watching and not actually doing it yourself, you're going to have to painfully sit here and watch me type in all these numbers. So you might as well just be typing them in with me at the same time. Because again, as I've said many times, how do you learn? You learn by doing things. You don't just learn by watching. And if you've gotten this far in life by just watching, well, then maybe you're different from me, but most of you really need to be doing to learn. And hopefully I'm typing all these in my calculator correctly, but we'll see. So I'm going to go over to L3. I'm going to go up. I press enter, so I have that black box blinking there. And I said I was going to do express minus regular, so I'm going to do L1 minus L2. Okay? All right. So back up here, I said it was express minus regular. I said it was going to be, so mu d will be equal to 0. Pretty much in all these problems, we're going to have a difference of 0. So I'm doing mu d is less than 0. I'm doing a one sample t-test for means, and I want to say that it's a matched pair. So for my random check, they were both randomly selected and randomly assigned. All right, my normal check. So I'm going to have to look. This doesn't say anything about the population being normal. The sample size is not bigger than 30, so I'm going to have to look at a graph. And I'm looking at a graph of that L3. Okay, so the box plot shows no skew, no strong skew or outliers. Okay. Independence. So I could say assume 150 times in a week, but I know there's an infinite number of times in a week. I mean, even if you, like, where would you stop? So if you're looking at the hours, well, then you have the minutes, and then you have the seconds. Like, there's just going to be many, many times in a week. Okay, if you want to say 150 times in a week, that's fine. All right, we're going to go to stat. I'm going to go to tests. Again, if you want to do it using the formula, you can run that 1var stats, but you would run your 1var stats on the list 3, and that's what you're using. So this would be my mu d, and this would be my sx that I'm using. I'm going to go to stat tests. I'm just using the t-test. I'm going to use the data option. This is 0. I'm going to put this to list 3. I'm going to use less than, and then I'm going to hit calculate. So you're going to write mu less than 0. You're going to write all this stuff down for me. If you ended up doing this the opposite way, your test statistic is just on the other side. So if you did greater than 0, which I did in the notes that I'm putting online, I just did the opposite way. So you'll see that I get greater than. Just give me the degrees of freedom also, so they're 14. All right, so then from all this stuff right here, so this, I was using 0.05 up here. So the p-value is less than alpha. So reject HO. There is enough evidence to say the express lane is faster on average. If you would prefer, so for this part right here, if there's enough evidence to say that the true mean difference in seconds of the two lanes is less than 0, that's fine. I just kind of went back to what the original question is: the express lane faster? Okay. All right. This next section here. So it's about, we've got using tests wisely. So obviously tests are used in a lot of different fields. So we want to make sure that we're using them wisely. So carry them up. Doing it on the calculator is pretty easy. So you're just plugging numbers into the calculator. You can always plug numbers in the calculator, but do your numbers actually mean anything? So there's this idea here of statistical significance and practical importance. So sometimes, especially if we have a large sample, we might get results that are statistically significant, but they're really not that important. So here's an example. We've got a large school district. They're implementing a new math curriculum. They randomly select 500 students. So everybody got the old curriculum, and then the next year everybody gets a new curriculum. So they randomly select 500 students. And when I say everybody, I mean everybody, not just those 500, like everybody in the school. And look at their change in curriculum. So the mean improvement was 0.9 with a standard deviation of 12.01. So calculate the test statistic for this hypothesis. So you could do it by hand, you could type it in the calculator, either one. So you get this, we get a p-value. Are the results significant at the 0.5% level? So yes, my p-value is less than alpha. So I would reject HO, and I would conclude that there is a mean, the mean difference on average has increased. So it does look like the new curriculum has increased the scores. So then there's two questions right here. So I just said it does look like it. But can we actually say that? Well, the problem is here is this was not really a well-designed experiment. So I have no way of knowing if these kids just improved their scores because they were taking the test for a second time. So I don't know that it was from the curriculum or not. I don't have a group that didn't get the new curriculum just to see if there was an improvement, okay? That being said, let's just say, okay, but we still saw a difference there. So is that difference of any importance? Well, so let's just think here. So I'll tell you this. Like your Keystone Algebra 1 scores, so to be proficient, you need a 1500. So if we have a 0.9 improvement, is that really a big deal? So in this case, a 0.9 difference is not really a big deal. That's not really, showing a drastic improvement in Keystone Algebra 1 scores or in these math scores, these standardized test scores. We are observing, we're finding out that that difference is so big because our sample size is so big. If that sample size was smaller, this number down here would be larger, thus making this one, this one down here, let me just do it. So like right now I have 12 divided by the square root of 500. Let's say if I had a smaller sample, so that number would be bigger, so then when I divide, this would be smaller, so I wouldn't be so far away from 0. Like this is a standard score, so I wouldn't be all the way out here like in, the 1.5 standard deviations away range, okay? So it's just because of that large sample size. All right, don't ignore lack of significance. So that 5%, that alpha of 0.05 is used a lot. And sometimes, like we just saw, you can only detect differences with large sample size. And maybe, depending on what you're studying, maybe that a small difference, so maybe a difference of 0.9 is a big deal. So if you were designing a study, you want to make sure that you have a high power of detecting the difference in the size that you have. The other thing I'll say here too is that like if you have a p-value of 0.0501 and your cutoff is 0.05, so you're just going to say, well, fail to reject because this is higher. Well, it's really not that much higher. So like I don't know, maybe those results are worthwhile to somebody, and maybe somebody would look at them differently and say they do want to reject and they do want to conclude HA. So, don't fall into the trap that that's your cutoff and that is what it is. There's some gray area here. Statistical inference is not valid for all sets of data. So, when I do these 4 steps, I can't correct for errors in the data collection. So here's an example. I want to know the average GPA for students at my school who are enrolled in AP Statistics. So I just talk to everybody. I conduct a census and I talk to everybody. So is it appropriate to construct a one-sample t-interval for the population mean? No. I have the whole entire population. I can just find the actual number. I don't need to create a confidence interval. I know what the answer is. I don't need a range of values. I know the answer. All right, beware of multiple analyses. So this one right here is kind of saying, so you take a sample, reject HO. Take a sample, reject HO. Take a sample, reject HO. At some point, you're going to take that one sample that's going to give you an error, and you're going to fail to reject. All right? Because those samples do exist. They are not likely for you to capture them, but they do exist. So let's say we have 20 significance tests, and in each case, the null hypothesis is true. What's the probability we avoid a type 1 error in all 20 tests? Assume a 5% level of significance is used. So in one test, the probability we make a type 1 error is 0.05. The probability we avoid it is 0.95. So what's the probability that we avoid it in 20 tests? I want to raise that 0.95 to the 20th. So the probability that all 20 tests, that I don't make an error in all 20 of those tests is 0.36. So that means the probability that I made at least one type error is 1 minus that, so it's 0.64. So there's a very good chance if I keep repeating the same thing over and over and over again, at some point I'm going to make that type 1 error. And then what am I going to do? Like, we know that could happen, but like the majority of the time I'm not making that type 1 error. So what are you going to do if you get confused? All right, so just kind of like need to do a study and then just roll with it. All right, there's your homework.